Well folks, Sean back here again from SMD Methods. You're very welcome into this fourth video on the series which explores the setup and different configurations for a Formula Student car application. In the last video we finished off the discretization or the meshing of the fluid domain in which our airfoil and front wheel tyre is sitting, and in this video we're going to move on ahead and we're going to program the Fluent solver, program the physics for this setup. And before I move on into the setup, there's a couple of things that I'm going to bring to attention. A lot of the parameters that we have created in what was the geometry and the meshing we're going to keep, and we're going to really use these as driving parameters. When we move into this Fluent solver now, I'm going to apparently double up on them. I will double up on them because what I want to also use is, even though I'm outputting some of these parameters here, I want to maybe use them outputs as inputs into the Fluent solver. So when I make a change one place on Workbench or within this kind of analysis, this A analysis, when I say A I mean this here, and the project schematic, this A analysis, I want to make it in one place, and then I want it to kind of filter out through each of the individual components of the analysis. All right, so that's something there you're going to see in this video happening, but I will tie it together again when we come back into the parameters. The other thing that I was thinking about here was in the meshing, which I'm just going to open up briefly, is I did do it in the STEM Racing series. I don't believe that I did it here in the meshing. Now this is the first time I've opened up the meshing since. And it was a few hours ago that we had done this, and I see this folder seems to be populated. Connections, contacts, yes. See this contact region, see these contact regions, I generally always delete them. Right? They don't really ever add much to the to the system. And what I can see here on this one now that I am looking at it is that it is noticing here that I have some sort of a contact region between my buffer region and what's the track, where I don't really have a contact region there. So it's gonna, this section here should be a track. It's probably gonna come up maybe with probably as an interface. More so if it's a contact region, it'll come up as an interface, which is not an interface. So what I'm gonna do is I'm gonna delete that out. Just delete that away. I shouldn't have to regenerate the mesh from this. Connections, so there is no connections effectively. The mesh is still all there, but what I do need to do now is I'm going to come into mesh and I'm going to update that. So I'm going to send this down to Fluent. Mesh translation to Fluent was successful. So hopefully whenever I look at my boundary conditions, I'll not see any interfaces other than the interface that I want to see, which is between the near field meshed face mesh and that buffer region. So opening up setup again, always have a look down in your properties to see is there something there that you could change, which I don't see anything there. That precisions, let me just move my controls, is on to double. When I open up the window, it's going to ask me, do I want to do it anyway? I have 24 processors on this computer, so what I'm going to do is I'm going to run with 12 solver processes on it. That's half of them. Why 12? Well, simply because it's half of them. What's the best number? Don't know. It all will, it's kind of a balancing act, I believe, between your CPU kind of processing and the amount of RAM that you're running as well. So what I typically do is I also look at the CPU performances. Now that's brought up with a Control-Alt-Delete and then onto my task manager. So when I hit Control-Alt-Delete, I do not know what's going to happen to my video, so I'm going to try it. If this blanks out, bear with me. Control-Alt-Delete. Now I click Task Manager. The video seems to still be running, so hopefully it's kept going. I'm going to look at performance, and then I'm going to open up my resource monitor, which opens up a new window. I can X out of that now, and now what I can do is I can look at my processor here, 11%, 10%, and so on. So each of my processors are going to be running here. So there's virtual ones in there as well. but this is what we're going to look at. So we'll look at our CPU usage, and we'll also want to look at the memory usage here as well. So generally there, if the CPU are struggling and I have plenty of memory, we can allocate more solver processes or parallel processes to this, and vice versa. The memory is struggling a little bit and the CPUs aren't. We could take maybe some CPUs away and leave less work on the RAM to do. Okay, so let's just drop that down. And generally, we'll look at that as the flow field is being solved. All right. So let's go down this here. This looks to be loaded in okay. And on the outline view, I generally work from the top to the bottom, albeit that I'm going to write in a couple of report definitions before I go in and change any sort of boundary conditions here, which I'm going to need. But in general, everything looks good. I'm going to run a steady state. Why not run transient? People say, oh, don't run transient. It's too hard on the CPU, or it's too much computational effort required for what you get out of it. That's not completely true. There's no point, I would say, running a transient application on this where we're for 2D analysis on an airfoil. It's 2D, so it's assuming an infinitely long wing here. So what we're going to get off of this is only just a cross-sectional snap of a section of the wing. We're not going to get, results that we can accurately and adequately rely on. So I wouldn't be so worried about going transient on a 2D analysis here, unless you're looking to, output colors for directors or such. You want to see nice swirls and this and that happening around it. So I would go the transient effect on a 2D airfoil application is more for aesthetic purposes than for any sort of meaningful results. So the steady is going to be fine for us here. Certainly when we move this onto a 3D analysis, or maybe into particular sections of the wing, taking in end-plate effects or this or that, surely let's go transient on it. But at the minute, steady is going to do me lovely. Pressure base, we're nowhere near compressible flow on this, so pressure base is grand. My models, for my viscous model, I'm going for the SSTK Omega, which is here. The Spallert Almaraz, could be another healthy alternative if you wanted to look at it. But again, that all depends not only on your Reynolds number as such, or your inlet velocity. If you're going, like I could say, it's under 500,000, or it's at 250,000 is what my Reynolds number is at. Surely this is laminar. That's only so good if you're relying purely on the free stream velocity. But how that interfaces with the actual aerofoil itself, could result in turbulent effects, or certainly transitional effects even at them lower Reynolds numbers. So the flow regime itself, I would say, isn't completely independent of the surface that the air is flowing over, or the fluid's flowing over for that matter, and that it's not completely dependent on the velocity, the density, the chord length, and the dynamic viscosity of the air. Each aerofoil there will I suppose pull out certain characteristics of the flow field for a given velocity. So yeah, Spallert Almaraz is fine if you're 100% sure of how the fluid flow is going to interact with the surface. If you don't know, K Omega is not bad. Certainly you can go transition for equation ones, which would capture an awful lot. But I'm happy enough to try K Omega 2 equations once that we use the SST version of it. Okay. So again, yeah, boundary, multi-phase, get out of the models. Our cell zones, no harm checking. As shown here that I have two cell zones. The reason I have two here is because I have two completely different surfaces. They're joined together as one part to make the meshing a little bit more continuous, or a whole lot more continuous, but I still have two independent surfaces. That's why I have two cell zone conditions in there, but that's fine. Once there is an interface boundary between the two of them, which I'd be hoping to see in the boundary conditions, so interior total flow region, that's just the buffer region, that's the flow region, buffer region dot one is interior outlet. It's not even in, there's an interface region there. You see this buffer flow field. Let's get a quick look at this display. Turn all them off. Region display. Right, so that's just this, the face splits. Region 1. Yeah, that's that interface in there between the near field and the buffer region. And that there is just in as an interior. It's not giving us a option to go as an interface, but that's fine in as interior there. Yeah, so there is parameters that I need to change in these here, or I need to edit, for instance, my velocity and all that, but I just haven't defined them just yet. I'm not putting them in as constants. I want to put them in as parameters. So I'm going to go on ahead and I'll write them in the named expressions. But before I do that, just to make the workflow with this a little bit smoother, I'm going to go into report definitions first. I'm going to create a few report definitions. First, force, X, force, and this is going to be on the wing. So I'm going to write this here as, yeah, no, I'll actually keep it as main element in this, because then I'll do X force flap, X force other flap, and then I'll do a total drag force on a wing, which will be the sum of all of them. In the X direction, don't need either of them, and I'm going to measure that on the main element. Okay, new force report, force, this is going to be the Y force on the main element. Nothing on the X, all on the Y, no report file, no report plot, and it's on the main element. Okay, I'm going to do another one, force report, force, let's go for X force on the wheel and tire, call it a tire, that's the outside surface, all in the X, nothing there, nothing there, that's on the tire. This will be the drag, effectively, on the tire. Maybe a wee bit of lift on the tire, surely. I'd expect to see some sort of accelerated flow over the top, even though the tire's going kind of in the opposite direction, turning in the opposite direction of the flow, which we will also model. May as well put it in. Force, again, let's go Y force on the tire, 0 and 1. Don't need a report or a file or a plot, and this is on the tire. Okay, that's all good. Okay, let's close that down. Now, what we can do is come back on into our named expressions. So I'm kind of making these up as I go along now, really am. I haven't tried this now before. I have a general idea of what I want, so please bear with me. Velocity at the inlet, I'm going to put this in as a constant value at the minute. If I can recall from our Y plus 2 first cell, we worked at, I think it was 20, and I shifted it down to 18 meters per second. Okay, input parameters, I want to input that from the design point table. Okay, leave my inlet new, I want to output my force drag for the wing, and I call it a wing here as opposed to a main element because I'm not really worried about what the drag is going to be on each element of the front wing whenever I start adding my flaps on. I just want to know what the total wing is going to be. So at the minute this is going to be equal to my X force, not down here, X force on the main element, because the main element is the only part of the wing that I have at the minute. I'm going to output that. Okay, new, let's go for FL on the wing, and that there is equal to my Y force on the main element. Let's output that. Okay, let's go for new, let's try our FD total. FD total is going to be equal to my X force on the main element plus X force on the tire. Let's output that. Let's go for a new FL total. Got my FL total. That's equal to the Y force on the main element plus the Y force on the tire. Output. Let's now go for L over D. So I'm going to L hyphen D hyphen wing, just the wing L over D. This is going to be FL wing divided by FD wing, output parameter. Total L over D, no, I'm not going to bother with that just now. Right, what else do I need to know? I also want to know the angular velocity of the tire. So what else? I'll need to put in the wheel diameter for that. Now, this is one of the cases I've already specified what the wheel diameter was out of the geometry. So I have to write wheel diameter in this here as well. I'm going to use that as an input, I believe, and then I can assign the input out in the design table to be equal to what that input was out of geometry. So maybe you might just stay with me for this here. So it's not even wheel diameter, it's tire diameter. Now the tire diameter, I'm going to put this in as a constant, and then I'm going to update it to be a formula. But the tire diameter for that Hoosier tire, it was on a 10-inch wheel, was 414.02. So put it in meters maybe. Let me see. I put it in meters. 0.41402, and then let's specify that as meters. I'm going to use that as an input parameter. Now, so I'm inputting this already in two locations. If I look here in parameter set, there's tire diameter. But what I'm going to do, I'm going to see another tire diameter input, and I'm going to say you make that equal to P3. So I'm only going to change it in P3. It's going to update that, and from that, it'll update Fluent. Okay. Now, once I know the tire diameter, I'll know the tire radius, and I know the free stream velocity, the velocity at the inlet, so I should be able to calculate, which will also be, by the way, the speed that the linear velocity of that tire at a certain radius is going to be, given we have no wheel slip, say, a wheel spin. So let's go for new, and let's go for omega tire. I'm going to just keep that a small o, just because I have velocity here as a small v. So omega v is equal to omega r, which means omega is equal to v divided by r, which is going to be velocity inlet divided by my tire diameter divided by 2. Now, if I hit this, that's in per second, so that's in radians. So what I need to do is I need to multiply this by 1 radian to make it radians per second. Refresh that. There you are, per second radians, or radians per second. I don't need to use that as an input or an output parameter. Okay. And for my boundary condition for my tire, I'm going to make that a rotational element. So it's a moving wall, and it's going to be rotational. I also need the center of my rotation, which means I'm going to need to know my X position of my tire. Again, I'm going to put this in as a constant. So again, this is another one. Wheel to leading edge ME for the main element, 907. I have that because the leading edge is at 0, 0. 907.01 back is where it is. So I'm going to write this in as 907 or 0.90701. That's in meters. And I use that as an input parameter. And then after this, I'm going to assign the geometry specified X dimension, leading edge to the front of the tire, to drive this one. X position tire, Control C. Let's make sure that's good, 907 meters, okay. And then we also need new Y position tire. And that one was hub height 205, 0.205, specify that in meters, and use that as an input as well. Okay. Should have maybe refresh that first. This one's taking a wee bit of time to come in. Feel the fan is kicked up big time on this now. I'm going to use this as an opportunity to think of if I need anything else to run out. I don't believe I do. Anytime that I would have done angles of attack before, I would have altered the direction of the inlet velocity air coming in. So I would have had an expression for angle of attack and then a sine and a cosine to calculate the lifts and the drags and so on. But because I'm going to alter the angle in the geometry, I'm just going to assume that the velocity is coming in purely in the x direction. We're on a flat road, in other words, so the air is going to be moving parallel with the road. And I think maybe that should be it. If we need another one, we're just going to have to go back in and make them. Boundary conditions, let's see what we have. So the inlet, let's now edit the inlet. And we're going to go for magnitude and direction. Our velocity magnitude is vel inlet, which was 18 meters per second, written there as a parameter, all in the x direction. Apply. Close. Now these are all interiors, outlet. Let's just confirm that that is a pressure outlet, which it is, and zero gauge pressure. All that looks okay. These are all inlets, interiors, not inlets. Now the wall of the ME main element, let's just make sure that that is a no slip condition and it is stationary. No slip and stationary, all good. Now the track, however, edit. Track should have a no slip condition as well. However, it is going to be a moving wall with a velocity of the inlet all in the x direction, and it's translational. Apply, close. The tire, on the other hand, edit, is also going to be a moving wall, but it's going to be rotational. No slip, moving wall, rotational. Radians per second is what we needed, which is omega tire now. The origin, x position tire, y position tire, apply. Okay, that's it. Methods stable coupled, pressure, velocity, everything's second order. Okay, controls, there's no relaxations in this. Report definitions are all done. Our monitors, residual. I'm going to drop these down to a much more competitive value. All look good. Yep. Okay. I'm not going to set out any other convergence conditions with respect to lifts or drags or anything like that. The residuals are going to be fine for this application. Initialization. First, I'm just going to check my standard initialization. Check that from the inlet. 18 meters per second looks pretty good. Let's initialize that. Okay, taking a wee bit of time. See what this comes back with. Right. Usually when I threaten that I'm going to pause this, it seems to hear me and it moves a bit quicker, just like that. So there we are. Initialization is done. Now down into the calculation where the fun happens. So number of iterations, let's go up to 1,000 here. 10,000 here all night. Reporting interval, every 10 is fine. Must be running a few background processes here. How do we get 40% on that? CPUs 12%. This is just getting her tight here now at the minute. That one in red that's shown is not responding. That there is our, there we're back. That is Fluent. Report intervals 10 and 10. All right, that's it. Let's go. Let's hit calculate and see what we are going to get back with here. I feel better now when I see the residuals come up and see them moving. And then what we'll do is I will hit pause because this could take a wee bit of time. Albeit I wouldn't expect that it would take more than maybe half an hour for this. We do about 800,000 elements on it. The meshing is pretty good, so hopefully it will find itself converging relatively fast. I expect the X and the Y velocity components to come down very fast and be below our residual limit. Continuity, I don't think is going to drop much more than e to the power of -5, probably at the best. And K and omega will probably drop in maybe down to the -6, -7. But I just want to see, yeah, this is what I was expecting. The wall motion has a significant normal component, 162 faces. We're going to see there, that's just a warning, it's not an error. That's more than likely where our tire wall has come down onto the track surface and we have a lot of pinching in there. And that's just trying to pick up that motion. So that motion is coming around. If you recall, we squished that wheel down into the track. So I believe there that's what one of the results are, is that we're getting this warning out of it. Not be written again, which is completely fine. I just want to see continuity start dropping here before I pause this, in case I have to stop it and make a quick comment on what's going on. Let's just wait for the next one here. Yeah, it's just coming down nicely now. So we could see there, this is like the Y velocity is already past the residuals. Yeah, it's dropping by 4. It's dropping nicely. Yeah, big drops there as well. So I'll tell you what I'm going to do. I'm going to hit pause on this here. Surprisingly, we're nearly a tenth through this already, so we're moving fairly fast. It's now 5 minutes past 11. I'll keep an eye on this and I'll come back as soon as it has completed. Okay, see you in a bit. Okay, everybody, back again. It is now 21 minutes past 11, so that was 16 minutes to take the run. Calculation complete. So what we'll do now is we'll have some look at the contours before we move back on into the workbench and into the parameter table to see what the results of the lift, the drag, the L over D and so on are, even though, you know, the values will be roughly uninterpretable to us until we look at comparisons of this particular airfoil at different angles of attack, or maybe even at different chord lengths. So into graphics, let's go to contours first. By the way, if you're interested, there's the residuals out over 1,000, and they actually came down, you know, very well. Like I don't think I've ever seen continuity down that far in analysis that I've done before. Maybe it is because that mesh is so resolved in next to the aero surface. Pressure is always prompted first when you open up contours. I don't know why. I like always go to velocity first. Maybe it's just more interesting looking contour, and get you more motivated looking at it. So let's go for contour. Velocity. Go for magnitude and let's see what we have here. Right, so we had a 1.8 meter or 18 meters a second in our inlet here in the yellow, and very much so as expected. Yeah, we'll have a zero velocity in here. We have a slight acceleration over that leading edge. We have more acceleration coming down under here, which seems to be 33%. Very big separation region, obviously here to the back, where our boundary layer breaks away. We're losing too much energy off of the flow by the time we get to here. That acceleration has died off very quick with this adverse pressure gradient obviously building here, which has detached the flow and hasn't been able to be reattached. We're at too low of energy there, where the top surface here we can still see a very low pressure region here, which should be giving us our very low velocity region there, which means we still are generating some downforce pressure off of the top, even though we have a big waked drag region here. Seems to be maybe some level of recirculation here, which no doubt is being contributed by the spinning of this wheel and tire. and then of course the big zero velocity or low velocity region right in behind that wheel. We see that wake coming off. Again, we have a rolling road here, mixing road, and these sort of reactions here we can't really rely on because we're going to have a car body, and a floor to work with here to treat this airflow to continue on. Okay, but nonetheless, very interesting looking contour, especially what we have in here. Now, I will always say it's never as interesting as the turbulent energy. Contour is always, in my opinion, the nicest looking contour, but let's get to that and see how we go. You can see the values in there a wee bit better. All right, let's look at pressure next. So I'm going to hit that save display, close that, right click contours, new contour hyphen, let's go for pressure. So static pressure. Okay, it always tends to be a good bit more sparse. Let's see, the loss of the vector contributes to that. See the higher static pressure here, which is obviously associated with the lower velocity region, and then obviously the lower pressure here to the higher velocity region as we accelerated over the nose. And again, we're changing. So again, we're changing roughly, adverse to the velocity gradients. So under here we have a region of low pressure, again relative to the ambient pressure out here, giving us some downforce, and then a slightly higher pressure here, again contributing to that downforce. See our effect of our wheel and tire here. We have a big high pressure region, obviously, where the air is nowhere to go. So again, this is on 2D. In 3D, that air is going to be coming out by the side. We'll be washing out, we'll be washing in, we'll be tumbling it around. This is really just to give some sort of an indication of the air coming off of that airfoil, the treatment onto this, from a 2D perspective, which is going to be always very limited. But noticeably enough, we could see a low pressure region here over the top, which makes sense because we have accelerated flow, but it also means there that the wheel is contributing to lifting the car off of the road, which needs to be dealt with. So if we can maybe take air away from this, lower the energy of the air here, we might allow the higher pressure air to take more of a hold over the top of this wheel. So these are certain wee things there that we could maybe look at and alter the profile and the chords and the angles of attack of this front wing to try to deal with. And again, we're back into a big low pressure region here, or in behind the wheel, which is odd as well because we have very low velocity in there too. Okay. Let's close this down and just save that again. And now let's right click this. Let's go into new. Let's go for contour K for kinetic energy or turbulent energy. Turbulent kinetic energy. And save display. This is always my favorite one. So yeah, very nice. Your turbulent wakes here, especially coming off the back. So this is that zero velocity kind of tumbling region, if you like. We're picking up a wee bit of turbulence and obviously coming over the top of the wheel. But we see the wheel maybe drawn in a wee bit here, and again that sort of a wake pattern coming off the back of high turbulent kinetic energy in this region here before it drifts off again. But we definitely have a lot, maybe what you want to call some dirty air coming off the back of it here. Okay, so there are the three main contours that I wanted to look at. And I'll close that off. We can look at vectors as well, will do no harm. So let's look at vectors for velocity. Velocity, magnitude. I have nothing selected in here. Scaling, skipping. I'm going to skip these down because we're in a very dense region here. Skip it down maybe by 10. See what this comes out with. Yeah, so there we are. Some vectors going top and bottom. See what's happening in around the wheel. We can see it tumbling around here, obviously. So we see our opposite flows. Here we have our vectors coming off the trailing edge of that front wing, but what we can also see here is velocity vectors coming back the way, obviously thrown down from the effect of the tumbling here, the swirl that we have in behind in the wake of that, in the wake here of the airfoil. Also have the effect of the tire. We should see, if we look to the rear of the tire, we could see the tire pulling air up, or pulling some velocity, some flow up with it as it scoots around, and that there then is obviously being overcome very quickly by the faster, higher energy moving air this way. Down here in the bottom, yes, this regardless of the what you might think, apparently here, that this wheel could be pulling air down and into the ground with it. It has nowhere to go, so it's coming into kind of a dead region. Again, this isn't really going to be the case, because in a 3D scenario, it's going to have room to escape out of the sides as that air coming on the underside of the airfoil meets some of the downwash, maybe from that tire, and it will escape side to side. We can't show that here on this kind of planar analysis, but again, it gives kind of an effect of pinch points maybe, and I suppose this here is one of the more significant things. This, from an aerodynamic perspective and how we design the front wing, I think this here region is probably the most telling, where we see the separation occurring here, which means there that we needed some way to inject some high energy air back into this region where we've lost energy very fast, to re-energize it, keep the flow attached onto the aero surface, and keep maintaining some downforce. All right, so let's close that up. Plots. Then we'll go for an XY plot, and what I'm going to do is look at the pressure coefficient on these. Pressure coefficient, let's look at that on the wall main element, and we're going to be looking at the direction function, save and plot. All right, so here we do see the adverse pressure occurring against the top surface and the bottom surface. So yeah, this single element front wing at that angle of attack for that velocity isn't optimal. All right, so our job is to find out how to optimize it, but the first thing what we need to do is just need to understand what the angle of attack itself is doing. Most of the lift is going to be generated at the trailing edge of the wing, more so than that leading edge. So it is the trailing edge there that we want to deal with. So the angle of attack doesn't really have the same sort of effect that you might think that it does on lift. It is really the energy at the trailing edge that's going to have the most effect onto this. At the minute, we have no energy on the trailing edge. Pressure coefficient there is adverse, and that's apparent. So what we want to do is get more energy onto that. But I'd like to see, if I tuck the angle of attack down slightly, is the amount of energy that I'm getting at my trailing edge, is it higher or lower? Like what is happening to the energy as I change my angle of attack, as I drop it there? Because maybe I might want to keep that Epler E423 airfoil flatter and then let the flaps take up that sort of angle of attack. And indeed, I'd like to compare this against a Selig Donovan 7055 main element and see how that's treated. It's a kind of it's a less aggressive as far as a camber goes on it, and it might be more suitable for a main element, just to initially treat the flow, accelerate it under the front wing, under the main element, and let the flaps take it over from there, treat the air at its trailing edge, and then every subsequent trailing edge after. So a couple of things there to look at. So save that and close. All right, so what I'm going to do now is I'm going to close down Fluent. I'm going to save this for future calculations. Yes, when this drops out, I'm going to save the file, and I'm going to go into the parameters. I'm going to assign the parameters that I just created in Fluent to be driven by the earlier parameters of the same specification that were created in Discovery. So I only have to change them again in one place, and then they'll filter through into Fluent as required. And then that's it. I'm going to wrap up this video and hopefully get all this done by 45 minutes. So slightly longer there than the last one, but just a little bit more involved in this one. And then, yeah, we'll look about altering the angles of attack in the future videos. So this is taking a little bit of time. And I rambled on there a wee bit, just try to buy some time to let it finish up. It's not happening, so I'm going to pause it, be back in a second. There you go. I threatened to pause and it finished up again. Anyway, we can jump back, I think. It's just playing with me now. Right, I'm going to pause it for real this time. I'll be back when this is done. Okay, back again. Yeah, so that's that bit done. Back onto the workbench. Let's save up this project as it is. Done into the parameter set, and we can see here in the design point table. I'm just going to scoot it over here. I'm going to drive a couple of controls over here. I'm going to drop down. As we move this across, wheel hub, that's P6. What's that one? Wheel hub height. That was a design modeler specified, right height design modeler specified. Far field, there's all the meshing ones. Inflation layers, all meshing ones. 24. Now this velocity inlet, right, 18 meters per second. This is the first place I put it in. Tire diameter 0.4102, right, is given to me there in P8, P23. So I'm going to start over here in P23. Tire diameter I have as 0.41402. Instead of having that there, what I'm going to do is I'm going to drive that from here, tire diameter P3. So what I should do is be able to put that in as P3. Right, and that's automatically changed that up there into millimeters, as you'll see. So now all I need to do is change my tire diameter there, and it's going to update my tire diameter here. Now, same thing with X position of the tire and Y position of the tire. So my X position of my tire here is P4. Right, so let's go for that. Let's go for P4. 907.01, and it updated my units there to millimeters. The Y position of my tire here, I'm going to update that to be P6, driven by the geometry. Right, and then ride height, I'm going to say ride height is going to stay where it is at 42, and that's it. They're all done. Now, I do not have, it's probably because I should have looked at them before I changed my parameters. I scooted that far over and I just could have went a little bit further, but I didn't. So I'm going to have to update all these here again. So to update all them now again, it's just going to change some parameters that are away. So what I'll do is I will, well, that is the values there, right? So I haven't changed anything that's going to change them values. L over D minus 4.905, the drag force 4.0536, which is in the direction of the flow, which is fine. I'm generating downforce on that of minus 19.78 newtons, or minus 19.87 newtons. All right, I suppose for that angle of attack. I'm getting lift, I'm getting positive lift. Obviously, there's an awful lot happening there at that wheel, which is just rising everything up. And then my drag here is obviously much bigger because of a massive drag element of the wheel. So if you did want to estimate how much drag was coming off the wheel, it would be the total drag less the drag on the wing. So we're at roughly, what's that there, 71.6 newtons of drag just by the wheel itself. And same thing here with the lift. So I'm going to have 73 and then nearly plus a 20. So I'm nearly at 93 newtons of lift at that, which seems to be absolutely massive over that there. So we definitely have to do something with that flow going out over that front wheel. It's just wrecking the downforce. Right, so what I'm going to do is I'm going to stop this video, bid you adieu, and take it up in the next video. And what we'll do is we're going to enter in new points here in our design point by changing this angle of attack. I'm going to try that there at minus, no point going down. I think in the half degrees go minus 14, minus 13, minus 12, minus 11, minus 10, and so on. Actually, we'll just write them in and then we can do it after. Minus 14, minus 13, minus 12, minus 11, minus 10, minus 9, minus 8. And actually what I'll do is I'm just going to hit update all design points, Right, this is going to just start running through each one of these. Right, and then the start of the next video, hopefully all these will be completed and we'll be able to have a look at the results and jump in. Oh, I'll tell you what I'm going to do. Let me just stop this over here. Abort. So I no sooner started it than I stopped it, but I'll tell you why is because I want to retain all that data. So I can set any one of them as current and then go in and have a look at the contours for any one of them. So now that that there is set at current, let me just clear them messages so I'll be able to see when new messages come up. They're just X because I aborted it. Let's go again and update all design points. Right, so I'm going to let it run away this time. And as I said, by the time I have the next video started on this, hopefully this will have finished. So yeah, thanks again for the time. Do hit subscribe on it because when the new video comes out, you will get a notification. So hopefully I have your interest peaked in this. And you'd be interested in seeing where we're going to go with it. So thanks for joining me and looking forward to seeing you in the next video. Thank you.